When ground acceleration occurs during an earthquake, structures experience inertial forces defined by Newton's second law, force equals mass times acceleration. Traditional fixed-base design relies on structural stiffness to resist these forces. However, high stiffness results in high shear forces and significant interstory drift, leading to damage. The fundamental period, T, of a structure is inversely proportional to the square root of its stiffness. Resonance maximizes structural response and damage when the structure's fundamental period matches the dominant period of the ground motion. Modern seismic design employs two primary strategies to prevent this catastrophic match. The first strategy is shifting the structure's period away from the high-energy range of the earthquake spectrum. The second strategy is dissipating the input energy before it accumulates as damaging strain. Base isolation physically decouples the superstructure from the foundation, fundamentally altering the structure's dynamic response. This isolation layer significantly increases the structure's fundamental period, typically shifting it from a conventional 0.5 seconds to 2.5 seconds or more. This period lengthening moves the structure's response into the low acceleration region of the seismic response spectrum. The isolation system must support the full vertical load of the building while accommodating large horizontal displacements, often exceeding 300 millimeters. By reducing the acceleration transmitted to the building mass, base isolation minimizes inertial forces. This protection extends not only to the primary structural frame, but also critically safeguards non-structural elements and internal equipment. Lead rubber bearings, commonly known as LRBs, consist of alternating layers of high-damping natural rubber and thin steel shims. The rubber layers provide the necessary flexibility for large horizontal movement and ensure the structure possesses a recentering capability after displacement. The internal steel shims are essential for confining the rubber, preventing lateral bulging under the immense vertical load of the structure. A solid central lead core is the primary energy dissipation mechanism. This lead core is designed to yield at relatively low shear strain, providing hysteretic damping. During cyclic deformation, the yielding of the lead plug converts kinetic energy into thermal energy, simultaneously lengthening the structure's period and dissipating seismic input energy. Friction pendulum systems, or FPS, utilize an articulated slider resting on a concave spherical surface. This mechanism physically isolates the structure. During intense ground motion, the slider moves along the curved plate, causing the structure to lift slightly against gravity. This lifting action generates a natural restoring force, acting precisely like a pendulum. The restoring force is proportional to the structure's weight and inversely proportional to the radius of curvature of the plate. Friction between the slider material and the concave plate provides the necessary energy dissipation, converting kinetic energy into heat. Crucially, the effective period of the friction pendulum system is determined solely by the radius of curvature, independent of the structure's mass. Energy dissipation devices, commonly referred to as dampers, are designed to absorb seismic input energy. This absorption prevents the energy from accumulating as damaging strain energy within the primary structural members. The primary function of dampers is to significantly increase the effective damping ratio of the structure. Conventional structures typically exhibit a damping ratio between 2 and 5%. Damped systems elevate this ratio substantially, often reaching 15 to 30%. Hysteretic damping mechanisms rely on material yielding or friction, where mechanical energy is converted into heat through cyclic plastic deformation. In contrast, viscous damping relies on the resistance generated by fluid movement, where the damping force is directly proportional to the velocity of the structural movement. Fluid viscous dampers, or FVDs, operate using a piston moving through a cylinder filled with silicone oil or a similar highly viscous fluid. The damping force, F sub d, generated by the device is proportional to the velocity, v, of the piston raised to an exponent, alpha. For linear dampers, the exponent alpha equals 1, meaning the force is directly proportional to velocity. For seismic applications, nonlinear dampers are often preferred, utilizing an exponent typically ranging from 0.3 to 0.5. This nonlinear behavior provides a high damping force during high-velocity earthquake movements, but offers minimal resistance during slow movements, such as wind loading. Energy dissipation occurs as the viscous fluid is forced through small internal orifices, converting the kinetic energy into heat. Metallic yield dampers, including devices like triangular or shear plate dampers, utilize the stable plastic deformation of specially formulated low-yield strength steel. These dampers are strategically designed to yield and deform before the main structural elements reach their elastic limit. During cyclic seismic loading, the metal undergoes controlled hysteretic deformation, absorbing substantial amounts of energy through the yielding process. The specific stiffness and yield strength of the damper determine the precise force level at which significant energy dissipation commences. Metallic yield dampers function as sacrificial elements within the structural system. They are designed to be easily replaceable after a major seismic event, ensuring the protection and integrity of the primary load-bearing structure. Base isolation is typically reserved for critical facilities, such as hospitals, data centers, and high-value structures, where continuous operational capability after an earthquake is mandatory. Energy dissipation devices are broadly applied in both new construction and the seismic retrofitting of existing buildings and bridges. Isolation systems drastically reduce floor accelerations throughout the structure, but necessitate large displacement gaps around the building perimeter. Conversely, dampers effectively control interstory drift and reduce shear forces without requiring significant perimeter space. Hybrid systems combine the benefits of isolation bearings with supplemental dampers, achieving optimized performance by balancing period shift, acceleration reduction, and energy dissipation capacity. Although historically cost-prohibitive, base isolation is becoming increasingly viable for multi-story residential buildings located in high seismicity zones. For single-family homes, smaller modular dampers are being developed specifically to mitigate non-structural damage, which often accounts for the majority of repair costs. Future trends in seismic design involve the integration of smart materials. A key example is shape memory alloys, or SMAs. These alloys offer superelasticity and high damping capacity. Crucially, SMAs can undergo significant deformation without permanent plastic strain, potentially eliminating the need for replacement of the damping elements after a major earthquake event.